Let's wrap up the introduction to sequences by studying one specific sequence called the geometric sequence. I call this one the heroic sequence because it is so convenient to work with, and it pops up in all kinds of interesting applications. To understand the behavior of the geometric sequence, we're going to get some terminology out of the way. Let's begin with a couple of definitions. A sequence, A sub n, is monotonic if its terms are non-increasing or non-decreasing. So the vocabulary word we are defining here is monotonic, but we've got two maybe unfamiliar other words in this definition. Non-increasing. It sounds like it's decreasing, right? Non-increasing means it is either decreasing or staying the same. So the sequence may stay the same and then decrease, stay the same, decrease, so on and so forth. Non-decreasing is not necessarily the same thing as increasing. An increasing sequence is always getting larger term by term. Non-decreasing means it is either increasing or it is staying the same. These two situations are classified as monotonic. Now, maybe you've had a professor in the past that is monotone, a professor who always talks at the same level and there's not much inflection in their voice. That's kind of the meaning of our vocabulary word here. Monotonic is either non-increasing or non-decreasing. The second helpful definition is as follows. A sequence is bounded if there exists a finite m greater than 0 such that the absolute value of a sub n is less than or equal to m for all little n greater than or equal to big N, where n is some element of the natural numbers. Oh my goodness, did you get all of that? How about a picture? A picture will certainly help us to understand all that's going on in this definition. So let's plot a sequence where the horizontal axis gives me n, the position of that element in the sequence, and the vertical axis gives me the value of that term in the sequence. Now let's suppose that our sequence is initially very sporadic and it jumps around, but then it begins to behave and it settles down in a regular predictive pattern. So again, recall that on the horizontal axis, we have the subscript or the position of that particular element in the sequence. So in this case, the sequence is initially sporadic, but then you can see that it begins to settle down as if it is underneath a horizontal asymptote. The value of this particular horizontal asymptote will be associated with m. So there is a finite number m, that's what I have up here on the vertical axis, such that the value of the sequence term, the absolute value of that sequence term, is less than or equal to this value m. So as you can see from our picture, most of the blue dots are below that red dashed line. And specifically, they are all below that horizontal asymptote at a particular subscript. So in the case of my picture over here to the left, when the subscript n, the position in the sequence, is 5, every single following term of the sequence is below that horizontal asymptote. So there is some point called capital N, in this case it's 5, where every single value of the sequence stays underneath this m. This means that the sequence is bounded. Now think about the natural meaning of that word. It is bounded. It has an upper boundary line. Now let's put these two definitions together to generate a theorem. A bounded monotonic sequence converges. So if you have a sequence that has these two properties, it is monotonic and bounded, then it is going to converge. Let's look at a couple of pictures to better understand what's going on. Again, I'm going to assume that we are plotting the position of the particular element of the sequence versus its value. We are going to assume that the sequence is bounded. That means it's going to have some sort of upper boundary line, and we'll call that value m. One way for a sequence to be monotonic is for it to be non-decreasing. That is, it is either increasing or staying constant. So if successive terms of the sequence either have to stay the same or are increasing, and the sequence is bounded, because it can no longer go down here, it either has to be increasing or staying the same, it is going to converge. The limit of this sequence is going to be this value m. On the flip side, you may have a non-increasing sequence, which is like decreasing but not quite. So let's suppose that there's some sort of bounded value m, and our sequence is going to be non-increasing. So that means it can either be decreasing or staying the same. In this case, you can see how it is definitely going to converge. If the sequence can no longer increase past a certain point, it is either decreasing or staying the same, it's going to level out there at that horizontal asymptote m. So both of these vocabulary words, monotonicity and boundedness, will be involved in our study of the geometric sequence. So let's go ahead and define the geometric sequence next. You're going to love the geometric sequence. This one is definitely your friend. A common geometric sequence, or a geometric sequence with common ratio r, takes the form a sub n equals a times r to the nth power from n equals 0 to infinity. Notice right here, I just want to catch your attention that we're starting the position at 0. Instead of counting at 1, we're starting at position 0. So the first term would be ar to the 0th power. We're calling that term 0, or a sub 0. The next one, we would increment our index by 1. This is position 1. We would call this one a sub 1. The second one would be a sub 2, so on and so forth. Now, notice how this is defined recursively. As we progress from one term to the next, we are multiplying by r. So that is our common ratio. Recursively, we could say that each term is generated by multiplying the previous term by r. But the formula that we have here is stronger and more reliable. This is our explicit formula. To determine the convergence of the geometric sequence, the following theorem will be helpful. For geometric sequence r to the nth power, the limit as n approaches infinity of r to the nth power is 0 if the absolute value of the base, r, is less than 1. So in a geometric series where the common ratio is a fraction less than 1, the limit is 0. If the base is 1, since 1 to any power is equal to 1, then the limit will be 1. And here's the case that's set apart. If r is either less than -1 or greater than 1, then this limit does not exist. The most important concept that you want to obtain from this part is that if the common ratio is a fraction less than 1, then the geometric sequence converges. If the base is greater than 1, then the geometric sequence will diverge. Note that for positive r, the sequence r to the n converges or diverges monotonically. If we have a negative base, then we'll see that it converges or diverges by oscillation. And we'll look at a couple of examples of this vocabulary. In example 8, we are looking only at geometric sequences. The first one, we have 1/3 to the nth power. Notice in this case, the common ratio or the base here is 1/3. Since 1/3 is less than 1, then we could observe that the limit as n approaches infinity of 1/3 to the nth power is equal to 0. Therefore, the sequence converges. Because the base is positive, it is converging monotonically. To better understand that, consider the graph of the sequence. Notice you have an exponential function with a fraction for a base, so this is going to be a decreasing exponential function. In a more general case, we could say it is a non-increasing sequence. Because it is non-increasing and it has a limit of 0, it converges. So very specifically, we can say it converges monotonically. On example B, notice that we have a base that is greater than 1. When the base of an exponential function is greater than 1, you have an increasing exponential function, or more specifically, you can observe the limit as n approaches infinity of 2 to the nth power is equal to infinity. So if we imagine the picture of what this sequence would look like, we simply have an increasing exponential function. It is unbounded because the limit goes to infinity. So we could say, therefore, this sequence diverges. It diverges because the limit does not exist. And we could say it diverges monotonically. That is, it is non-decreasing, and in this case specifically, it is increasing. The next two examples have bases that are negative. So when we do our analysis, we want to consider the absolute value of the base. So the absolute value of the base here, the absolute value of negative 0.1 is 0.1. This is still less than 1. Since the base is less than 1, then the limit as n approaches infinity of our sequence is 0. Therefore, this sequence converges. However, it converges in an interesting and different way than the two examples that we've seen previously. If we consider evaluating several of the terms of this sequence, we would notice that this is an oscillating or an alternating sequence. That is, for an even value of n, we're going to have a positive output. For an odd value of n, we're going to have a negative output. So our sequence is going to do something like this. It's going to hop up and down, above and below that horizontal axis, yet it is still converging to 0. So the way that we describe this behavior, we say the sequence converges. Remember, it converges because the limit is finite. It converges to 0, but we say it converges not by, but with oscillation. A negative base causes an oscillating sequence. A similar result will be true for our last example. In this case, the absolute value of the base, negative 3/2, which is positive 3/2, is greater than 1. Which means when we find the limit as n goes to infinity of negative 3/2 to the n, we end up with infinity. This means that the sequence diverges. However, it diverges also in an interesting way. If we were to plot successive values for this function, because the base is negative, it's going to yield some positive and some negative outputs. And as n increases, the values of those terms of the sequence will also increase.